In coordinate geometry, one of the most fundamental operations is finding the distance between 2 points on a plane. This concept builds directly on the Pythagorean theorem we've likely seen in basic geometry. Let's consider 2 specific points on our coordinate plane. We'll denote our first point as x sub 1, y sub 1, shown in blue, and our second point as x sub 2, y sub 2, shown in green. Our goal is to find the straight line distance between these 2 points. This distance represents the shortest possible path from one point to the other. While it may not be immediately obvious how to calculate this distance directly, we can use the Pythagorean theorem by forming a right triangle with our points. The distance formula isn't just some arbitrary equation to memorize, it's actually a direct application of the Pythagorean theorem in a coordinate system. In the next part, we'll see how to construct a right triangle using these points and derive the distance formula by applying the Pythagorean theorem. This will give us a general formula that works for any 2 points in the coordinate plane. To find the distance between 2 points in coordinate geometry, we need a method that works for any 2 points. Here, we have point P1 at coordinates x1, y1, and point P2 at coordinates x2, y2 plotted on our coordinate plane. Let's create a third point P3 with coordinates x2, y1. This point has the same x-coordinate as P2 and the same y-coordinate as P1, creating a right angle in our construction. Let's draw a horizontal line from P1 to P3. Notice that along this line, the y-coordinate stays constant at y1, while the x-coordinate changes from x1 to x2. This horizontal distance represents the change in x-coordinates between our 2 original points. Now let's draw a vertical line from P3 to P2. Along this line, the x-coordinate remains fixed at x2, while the y-coordinate changes from y1 to y2. This vertical distance represents the change in y-coordinates between our points. By connecting these 3 points, we've formed a right triangle. The right angle is at P3, while P1 and P2 are at the other 2 vertices. This geometric approach gives us a way to calculate the direct distance using the Pythagorean theorem. The length of this horizontal leg can be calculated by finding the difference in x-coordinates. That's x2 minus x1. In our case, that's 3 minus -2, which equals 5 units. This horizontal distance is crucial because it tells us exactly how far we need to move horizontally to get from one point to the other. We can think of this as the run in the rise over run concept from slope calculations. For the vertical leg, we calculate the difference in y-coordinates, which is y2 minus y1. In our example, that's 4 minus 1, giving us 3 units. This vertical component represents the rise between our 2 points. Just as with the horizontal component, this vertical distance tells us precisely how far we move up or down when traveling between our points. Together, these 2 legs give us all the information we need to find the direct distance. So far, we've broken down the journey from P1 to P2 into 2 perpendicular movements, first moving horizontally by x2 minus x1, then vertically by y2 minus y1. This right-angled path isn't the direct route, but it gives us the components we need for our distance formula. The direct distance between P1 and P2 is shown by this straight line, which forms the hypotenuse of our right triangle. According to the Pythagorean theorem, the square of this distance equals the sum of the squares of the other 2 sides. With our horizontal side being x2 minus x1 and our vertical side being y2 minus y1, we can apply the Pythagorean theorem to find that the distance squared equals the square of x2 minus x1 plus the square of y2 minus y1. Taking the square root gives us the actual distance between the points. Here we have a coordinate plane with 2 points, x sub 1, y sub 1, and x sub 2, y sub 2. Notice how we've drawn a right triangle by creating horizontal and vertical lines between these points. This geometric approach will help us derive the distance formula. Our goal is to find the distance d between these 2 points, which is represented by the yellow line, the hypotenuse of our right triangle. Since we have a right triangle, we can apply the Pythagorean theorem which states that a squared plus b squared equals c squared, where c is the hypotenuse and a and b are the other two sides of the triangle. In our specific triangle, the horizontal side represents the change in x-coordinates, which is x sub 2 minus 2 minus x sub 1. Similarly, the vertical side represents the change in y-coordinates, which is y sub 2 minus y sub 1. Substituting these values into the Pythagorean theorem, we get the quantity x sub 2 minus x sub 1 squared plus the quantity y sub 2 minus y sub 1 squared equals d squared. To isolate d, we take the square root of both sides of the equation. This gives us the distance formula. D equals the square root of the quantity x sub 2 minus x sub 1 squared plus the quantity y sub 2 minus y sub 1 squared. This elegant formula works for any 2 points in the coordinate plane, regardless of their position. This formula is powerful because it directly connects algebraic expressions with geometric meaning. The differences inside the square root represent the horizontal and vertical components of the displacement between the points, while the square root itself gives us the direct path distance. The distance formula is actually just the Pythagorean theorem applied to coordinate geometry. Whether you're finding distances between cities on a map, calculating trajectories in physics, or solving geometric problems, this formula provides a straightforward method to determine the shortest path between any 2 points. When we're working with points on a coordinate plane, we often need to find the distance between them. This is a fundamental calculation in coordinate geometry that builds on principles you're already familiar with. Let's examine a specific example by plotting 2 points on our coordinate plane. We'll place point A at coordinates 1, 2, meaning it's 1 unit right and 2 units up from the origin. And we'll place point B at coordinates 4, 6, which is 4 units right and 6 units up from the origin. The question is, how far apart are these 2 points? The direct path between these points is a straight line. If we wanted to measure this distance, we could use what's known as the distance formula. But where does this formula come from? It's actually derived from the Pythagorean theorem. To understand this connection, let's construct a right triangle using our 2 points. We'll start by drawing a horizontal line from point A, moving only in the x direction. This horizontal line represents the change in the x-coordinates between our 2 points. Now let's draw a vertical line from the end of our horizontal line up to point B, moving only in the y direction. The intersection of our horizontal and vertical lines forms a right angle, which is crucial for applying the Pythagorean theorem. We'll mark this 90-degree angle with a small square. We've now formed a right triangle where the distance we want to find between points A and B is the hypotenuse. The horizontal side represents the change in x, and the vertical side represents the change in y. This geometric setup allows us to apply the Pythagorean theorem directly. Let's calculate the length of each leg of our triangle. The horizontal distance is the difference between the x-coordinates, 4 minus 1, giving us 3 units. We can think of this as the run in our right triangle. Similarly, the vertical distance is the difference between the y-coordinates, 6 minus 2, which equals 4 units. This represents the rise in our triangle. These calculations give us the legs of our right triangle. Now we can apply the Pythagorean theorem, which states that in a right triangle, the square of the hypotenuse equals the sum of squares of the other 2 sides. In our case, that's d squared equals delta x squared plus delta y squared, where d is the distance we're looking for. Substituting our values, we get d equals the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, giving us the square root of 25, which simplifies to exactly 5 units. This example demonstrates how the distance formula is simply the Pythagorean theorem applied to coordinate geometry. For any 2 points in a coordinate plane, we can always construct a right triangle and use this same approach to find the distance between them. Now that we have 2 points plotted on our coordinate plane, let's see how to find the exact distance between them. We'll do this by breaking the problem into horizontal and vertical components, which will lead us to the Pythagorean theorem. Let's start by drawing a horizontal line from our starting point at 1, 2. If we move horizontally, we keep the y-coordinate fixed at 2 while changing only the x-coordinate from 1 to 4. To calculate this horizontal distance, we subtract the x-coordinates. 4 minus 1 equals 3 units. This represents our change in x, which we sometimes denote as delta x. Now from our horizontal endpoint, we need to move vertically to reach our destination point. We keep the x-coordinate fixed at 4, while changing only the y-coordinate from 2 up to 6. For this vertical distance, we subtract the y-coordinates. 6 minus 2 equals 4 units. This is our change in y, or delta y. The direct path between our 2 points forms the hypotenuse of a right triangle. This is the actual distance we're trying to find. Notice how we've broken down a complex distance problem into 2 simpler ones that follow the coordinate axes. At the point 4, 2, we have a right angle because our horizontal and vertical lines meet at 90 degrees. This is crucial because it means we can apply the Pythagorean theorem to find the length of the hypotenuse. The distance formula is simply the Pythagorean theorem applied to coordinate geometry. It states that the distance equals the square root of the sum of the squared differences in coordinates. This formula works for any 2 points in a coordinate plane. Let's apply this formula step by step to find the distance between our points 1, 2, and 4, 6. We start with the formula d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. We plug in our coordinates, the square root of 4 minus 1 squared plus 6 minus 2 squared. Simplifying inside the square root, we get 3 squared plus 4 squared. These values match exactly with the horizontal and vertical distances we measured earlier. Computing the squares, we get 9 plus 16 under the radical. Adding these gives us the square root of 25. And the square root of 25 is exactly 5 units. So the distance between our points, 1, 2, and 4, 6, is precisely 5 units. Notice that while we had to travel 3 units horizontally and 4 units vertically, a total of 7 units if we followed the grid lines, the direct distance is only 5 units. This example demonstrates why the Pythagorean theorem is so fundamental in coordinate geometry. By breaking a diagonal distance into horizontal and vertical components, we can apply this powerful theorem to find exact distances between any 2 points in our plane. Let's look at how to calculate the exact distance between 2 points in a coordinate plane. Here we have the points 1, 2, and 4, 6 plotted on our coordinate system. To find the distance between these points, we'll use the distance formula, which is derived directly from the Pythagorean theorem. The formula states that the distance d equals the square root of the quantity x2 minus x1 squared plus y2 minus y1 squared. Let's substitute our coordinate values into this formula. For our first point, x1 equals 1 and y1 equals 2. For our second point, x2 equals 4 and y2 equals 6. Now we calculate the differences between our x-coordinates and y-coordinates. 4 minus 1 equals 3 and 6 minus 2 equals 4. These represent the horizontal and vertical distances between our points. Next, we square these differences. 3 squared equals 9 and 4 squared equals 16. These squared terms represent the areas of squares with sides equal to our horizontal and vertical distances. Adding these squared differences, we get 9 plus 16 equals 25. This is the square of our final distance. Finally, we take the square root of 25, which gives us exactly 5. This tells us that the straight line distance between our 2 points is precisely 5 units. This exact value of 5 units is important because it confirms what we might have suspected from the geometry of our points. We have a special case of a right triangle. Let's take a closer look at the triangle formed by our points and see why this result makes geometric sense. The horizontal side of our triangle has length 3, representing the change in x-coordinates as we move from the point 1, 2 to directly below 4, 6. The vertical side has length 4, showing the change in y-coordinates as we move straight up from below our second point. And the hypotenuse, which is the direct path between our points, has length 5, as we just calculated using the distance formula. Notice that where the horizontal and vertical lines meet, we have a right angle of 90 degrees. This is why the Pythagorean theorem applies perfectly to our scenario. What we've discovered here is the classic 3, 4, 5 right triangle, one of the simplest Pythagorean triples, where 3 squared plus 4 squared equals 5 squared, or 9 plus 16 equals 25. This example perfectly illustrates how the distance formula is really just the Pythagorean theorem applied to coordinate geometry. By understanding this connection, you can calculate the exact distance between any 2 points in the coordinate plane.